Hi, in this next concept in quadratic equations, we'll be looking at the idea of forming a quadratic equation with given roots. So we've already seen the idea of finding the roots given a quadratic equation. So now in a sense we kind of want to do the opposite thing. We want to start with two values which happen to be the roots, and we want to construct a corresponding equations whose roots will be these two particular values. Again, the idea is pretty straightforward, so let's just quickly look at it. So the idea is very straightforward. So what we are saying is that suppose you start out with two values alpha and beta which happen to be known, and you want to kind of develop that equation whose roots will be these two values alpha and beta. So it turns out that that quadratic equation, throughout the rest of the lectures on quadratic equations, I'll use QE as a standard abbreviation for the quadratic equation. The required quadratic equation must be of this particular, must be this: x square minus x times alpha plus beta plus alpha into beta equal to 0, which can also be thought of in a more general way in this way. So your required equation essentially is x square minus x into the sum of the given values plus the product equal to 0. So in fact, if you think about it, you don't even have to know the given individual values. All you need is the sum of those two values and their product. So as an example, so for a quadratic equation whose roots are minus 1 comma 3, I can directly say that that equation must be x square minus x into the sum of the values is 2 and the product of the values is minus 3. Right? So it's a pretty straightforward idea, and the proof is again very simple. So as far as the proof is concerned, we'll simply observe that a simple equation whose roots will be alpha and beta clearly is this. If I look at this equation is a second degree equation in x, and its roots are, by the rule of by the idea of factorization, the roots of the overall roots of this equation obviously are x equal to alpha and x equal to beta. So expanding this equation, I'll get something like this, which was our result: x square minus x times the sum of the roots plus the product of the roots equal to 0. And as I said, you don't even have to know the individual values. So for example, you can start combining the idea of symmetric function of roots with the idea of formation of a quadratic with given roots. So as another example, so again, just to take a very simple example again, if let's suppose alpha and beta happen to be the roots of alpha and beta happen to be the roots of this particular equation, and you want to form a quadratic equation whose roots are alpha square plus 2 comma beta square plus 2. So again, what we can do is so I could call this value alpha square plus 2 as some alpha dash and the value beta square plus 2 as some beta dash. So you want the value of alpha dash plus beta dash, so that will be alpha square plus beta square plus 4. We've already seen this in concept 2 that this is effectively the sum of the squares of the roots, so this will be alpha plus beta whole square minus 2 alpha beta plus 4. So alpha plus beta whole square becomes 1 minus 2 times minus 1 plus 4, so that becomes 7. So for the two values that you need, the sum of those values is clearly equal to 7, and similarly the product of the values alpha dash into beta dash, so that will be alpha square beta square plus 2 times alpha square plus beta square plus 4. So that is equal to alpha into beta was minus 1, so its square will be plus 1 plus 2 times alpha square plus beta square was this particular value. So that we've already seen is how much? 3 plus 4. So that gives us 1 plus 6, 7, 11. So the quadratic equation you want, so now effectively again my question is that you want to construct a quadratic equation whose roots are alpha dash and beta dash, where the sum of those values is 7 and the product of those values is 11. So the required equation must be x square minus sum of the roots times x plus product equal to 0. So as you can see, we were able to find that equation without actually finding the individual values alpha dash and beta dash. So it's a pretty straightforward concept, and we'll look at some more applications now. right? So it's again a pretty straightforward problem. Alpha and beta are the roots of this particular equation. The roots themselves will not turn out to be very simple values. For example, you get something like, if you use a quadratic formula, you get something like -1 plus minus root 17 by 4 and all. And again, now you want to construct quadratic equations, and you have 3 separate parts to deal with, right? So one approach for this problem, of course, is the whole idea of alpha dash and beta dash that we had introduced. So in each case, let's say this is alpha dash, this is beta dash. So if you want to construct a required equation, would require you to know two values, alpha dash plus beta dash, as well as alpha dash into beta dash, and both those values will turn out to be symmetric functions of alpha and beta, so their value can be found. Okay? So again, let's start. So in all the cases, alpha plus beta will be how much? Minus half, and alpha into beta will be how much? Minus 1. Right? So alpha dash is 2 alpha plus 3, beta dash is 2. And alpha plus beta is minus half, so this is minus 1 plus 6, so that's plus 5. Similarly, alpha dash into beta dash is 4 alpha beta plus 6 times alpha plus beta plus 9. So again, alpha into beta is minus 1, alpha plus beta is minus half. So that becomes minus 3 plus 9, so that is plus 2. So your required equation is, again, x square minus the sum of the values times x plus the product equal to 0. Right? So that's the first part. Similarly for the second part. Again, alpha plus beta is minus half, alpha into beta is minus 1, so this is plus half. Right, so x square minus x into sum plus product equals 0. So that is 2x square that turns out to be answer. One basic observation for the second part is that in the second part you are effectively reciprocating the roots. You had an original equation and you took a reciprocal of the roots, and the equation that you got after that, an interesting observation is that if you look at the sequence of coefficients over here, it's 2 plus 1 and minus 2, and if you look at the sequence of coefficients over here, it's again, so the whole thing can be written as this equation is identical to this particular equation. So effectively what has happened is that the sequence, when you reciprocate, take a reciprocal of the roots of the equation, the sequence of coefficients has got reversed. So you had 2, 1, minus 2, and now over here you get minus 2, 1 and 2. So this is something we can generalize later on, which basically means we are saying that if you start out with an equation ax square plus bx plus c equal to 0, and I take a reciprocal of both the roots, the new equation that will be formed will turn out to be cx square plus bx plus a equal to 0. And the last part is again similar, so we'll just quickly look at it. Now for the last part, you can obviously directly start manipulating it. There's some, you can kind of play around with it a bit also before you directly start finding the sum and product of the roots. So for example, this is alpha square plus 1 by beta, which is the same as alpha square plus alpha upon alpha beta. But alpha into beta is minus 1, so that is the same as alpha square minus alpha. Right? And also another observation is that 2 alpha square plus alpha minus 2 must be 0. So alpha square must have the value 2 minus alpha upon 2. So again, if I substitute that over here, alpha dash must be 2 minus alpha upon 2 minus alpha. So that is 2 minus 3 alpha upon right? So effectively I've shown that alpha square plus 1 by beta is the same as 2 minus 3 alpha by 2. So that is your value of alpha dash, and similarly for beta dash it will be 2 minus 3 beta by 2. So beta dash similarly will so again alpha dash plus beta dash must be again alpha plus beta was how much? Minus half. That will turn out to be 8 plus 3 11 by 4, and alpha dash into beta dash will be 1 by 4 when I multiply these two values. So that will be 2 minus 3 alpha by 2 into 2 minus 3 beta by 2. Right? So that becomes 4 minus 6 times alpha plus beta plus 9 alpha beta. Again putting values 4. Then alpha plus beta again was how much? Minus half. So that will be 6 into minus half becomes plus 3. And we have a minus 9. Alpha into beta itself is minus 1. So this will be minus 9. So 7 minus 9 is minus 2. So that is minus half. Right? So the sum of your required values is 11 by 4, and the product of the required values is minus half. So the answer should be x square minus x into sum of the values, which is 11 by 4, plus the product of the values, which is minus half. Which you can, if you want, you can simplify it further. So that turns out to be the answer, right? 4x square minus 11x minus 2 equal to 0. Right? Again, some fairly simple questions based on this concept. Just take a moment to go through the second question. So in the second question, in fact, the product of the roots is of, when you find that alpha dash into beta dash, that will obviously turn out to be root alpha beta, which is 1 by root of 1 by 36. So that will turn out to be 1 by 6. And what about the product? In fact, in the second one, if you want, you can also find the roots, because the equation is pretty straightforward. Because clearly the product of the roots, you have 36 over here. So, and you have 13 over here. So I could factorize it in this way. So I get so the roots themselves turn out to be pretty straightforward. Right? So your alpha dash, which is root alpha, will turn out to be, let's say, half. And the second beta dash, which is root beta, will turn out to be 1 by 3. So now effectively the question is that form an equation whose roots are half and 1 by 3. So the equation is, required equation should be x square minus x times sum of the roots plus the product. So if you were to simplify this, you'll get 6x square minus 5x plus 1 equal to 0. I think it's fairly simple. Again, you didn't necessarily have, in this case, because the roots themselves are very simple, we just found them. And but again, as we've seen through the previous example, even if the roots are not that straightforward, you can always find out, again, the more important focus is on being able to find out the sum of alpha dash and beta dash and the product of alpha dash into beta dash, rather than the individual values. Now in this third problem, we've been given two relations in alpha and beta, and on the basis of that, again, you want to construct a quadratic equation, right? So an observation is, so again, if you want to construct a quadratic equation whose roots are alpha square and beta square, you need alpha square plus beta square and alpha square into beta square, for which itself you need alpha plus beta and alpha into beta, right? So now the question is that from these two relations, how do you find alpha plus beta and alpha into beta? So that part, again, we've done a similar problem before in concept 2. So what we can essentially say is that since these two equations are true and alpha is not equal to beta, from these two equations I can say that alpha and beta must be the roots of which equation? 2x square minus 3x plus 4 equal to 0. That obviously should happen. Given that alpha and beta both satisfy, since these both relations are true, clearly alpha and beta both satisfy this equation. So if alpha has to satisfy this equation, what should have happened? 2 alpha square minus 3 alpha plus 4 should have been 0, which is true. Similarly, if beta had to satisfy this equation, what should have happened? 2 beta square minus 3 beta plus 4 should have been 0, which again is true. Right? And now it's pretty simple. Again, now I know alpha plus beta, that is 3 by 2, and I know alpha into beta, which is 2. So now alpha square is like my alpha dash, beta square is my beta dash. So alpha dash plus beta dash is alpha square plus beta square, which again will be alpha plus beta whole square, 9 by 4 minus 2 times alpha beta, which will be 4. So that's 9 minus 16, so that's minus 7 by 4. And again alpha dash into beta dash simply becomes alpha into beta whole square, so that becomes 4. So the quadratic equation that you want to construct, the sum of the roots is minus 7 by 4 and the product of the roots is again 4. So the equation should be x square minus sum of the roots times x, so plus 7x by 4 plus product of the roots plus 4 equal to 0. And then you can again simplify this further. So the final form will be 4x square plus 7x plus 16 equal to 0. So now this again is a constructing a quadratic equations problem, but it's you're kind of dealing with general terms, and also you have to be very careful in how you proceed with the problem solution, because over here again if you call this as alpha dash and then you call this value as beta dash, to construct your required equation what you need is alpha dash plus beta dash and alpha dash into beta dash, both of which are symmetric functions of alpha and beta and hence which can be evaluated in terms of p and q. But now the problem is that even if you just use normal algebra and directly start adding these ratios and multiplying them, the solution might become slightly, the algebra may become slightly involved. So first of all, again, you should try to make a certain observation on the basis of which the involved algebra might become simpler. So just think about that first. How can, this is your alpha dash again, but how can you simplify it a bit? So the idea would be that again I'll try to simplify the expression for alpha dash and the expression for beta dash would similarly get extended. So one observation again is that since alpha is the root of this equation, it will obviously satisfy the equation. So I can say something like this now: alpha into alpha plus p must be minus q, which gives me an interesting observation that 1 upon alpha plus p must be the same as minus alpha by q. This is important. Alpha was the root of this equation, so it will satisfy the equation, and I manipulated this equation to get this form. 1 upon alpha plus p must be minus alpha by q. So obviously then 1 upon alpha plus p whole square becomes alpha square upon q square. So from the first and the second statement, what you've shown therefore is that alpha dash, that was this value, turns out to be the same as alpha square upon q square. And now the form becomes pretty simple. So and similarly beta dash will be beta square upon q square. So again alpha dash plus beta dash becomes 1 upon q square alpha square plus beta square, which will again be alpha plus beta whole square, so that's b square minus 2 alpha beta. and alpha dash into beta dash will be alpha square beta square upon q raised to 4, and alpha into beta itself was let's check the steps again once again. 1 upon alpha plus b must be minus alpha by b. 1 upon q square is alpha square minus beta square, which is alpha plus beta whole square minus 2 alpha beta by b q square. And alpha dash into beta dash itself should be alpha square beta square by q raised to 4, and that should be q square upon q raised to 4. So that is 1 upon q square, right? So again, my required equation should be x square minus x into sum of the roots, which is alpha dash plus beta dash, plus product of the roots, which is q square, and then again if you want to simplify it further, right, so this observation actually reduced your algebra significantly, because otherwise you would have had to add these two values, reduce that entire expression in terms of p and q, similarly multiply these two values and reduce that expression in terms of p and q. Okay. Right, so again a similar problem, it's just that the algebra will again be slightly more involved, nothing to worry about as such. So again, let's start. So sum of the roots over here again is minus of a plus b, and product of the roots is a square plus b square by 2, right? So alpha dash again is alpha plus beta square, and beta dash is alpha minus beta square. So these values are actually pretty standard, so we can find them. Alpha plus beta square obviously becomes a plus b square, and difference of the roots, we've already seen this idea that alpha minus beta square happens to be the discriminant value, which is upon the coefficient of x square whole square 4. Okay. This will be a plus b whole square minus 2 a square plus b square If I simplify this, I'll get a plus b whole square, so that's a square plus b square plus 2ab. I'll just check the calculations again. Beta dash alpha minus beta square should be the discriminant value, which will be 4 into a plus b square minus 4 into 2, 8 into a square plus b square divided by the coefficient of x square square, that's 4. So I get a plus b whole square minus I'll get something like minus a square some calculation error is happening. Alpha plus beta was, let me just check the question again 2x squared plus 2 into a plus bx plus a squared plus b squared equal to 0. So alpha plus beta should be minus of a plus b, alpha into beta should be a squared plus b squared by 2. So your alpha dash is alpha plus beta whole square, which should be a plus b square, that's okay. And alpha minus beta square itself should be the discriminant value, which should be 4 into a plus b whole square minus 8 times a squared plus b squared by 4. So that will be a plus b whole square minus 2 times a squared plus b squared. That will be a square minus 2a square minus a square minus b square plus 2ab, right? Which is minus of a minus b square, right? So basically your roots, the roots that you need are alpha dash, which is a plus b whole square, and beta dash, which is minus of a minus b whole square. So again, what is alpha dash plus beta dash over here? A plus b whole square minus a minus b whole square, which is clearly 4ab, and alpha dash into beta dash will be, when I multiply these two values, will be minus of right? So these are again the sum of the roots. This again represents the product of the roots. So my required equation should be x square minus x times the sum, which is 4ab, plus the product, which is minus of a square plus b square. So that effectively is this. In some cases, this idea of transformations could also be useful in constructing your required quadratic equations. So we are looking at specific kind of transformations. So let's say alpha and beta are the roots of this original equation, and maybe you want to reciprocate each root. So you want to obtain an equation whose roots are 1 by alpha and 1 by beta, right? So over here what we are saying is that for this you can simply just replace x by 1 by x in your original equation. So in that case, what will happen is that you'll get a by x squared plus b by x plus c equal to 0, which when you simplify will give you cx squared plus bx plus a equal to 0. So this then would be the equation whose roots happen to be 1 by alpha and 1 by beta. As you can observe in this transformation, what you've effectively done is, again, you've reversed the sequence of coefficients. So you know the coefficient sequence was starting from the highest degree term was a, b and c, and now when you reciprocated your terms, it turns out to be c, b and a. So essentially what you just need to do is replace x by 1 by x. Another kind of transformation that you can talk about is a linear transformation. So by linear transformation I mean something like this. So if you want to construct a quadratic equation whose roots happen to be k1 alpha plus k2 and k1 beta plus k2, right? So again in this what you could simply do is you could replace x by x minus k2 upon k1, right? Suppose we label this as equation 1. Right, so when you finally simplify this, the whole thing as a polynomial, as a quadratic expression in x, that will give you your desired equation. Transformations are not necessarily only applicable in these two cases. So over here again what you were doing was you were reciprocating the roots, and over here the roots are undergoing a kind of a linear transformation. So in general you can talk about a general transformation, but that would don't have to really go into the general scenario. That will require some of the terms that we use in discussing functions. So I mean, in a lot of cases you will be able to reduce transformations which are not linear to a linear form also by simple manipulations. So we'll just look at an example in which we are applying this idea of transformation transfer. Right? So again, it's a pretty standard problem, the kind of thing that we started with. Each of the parts can easily be solved by the alpha dash beta dash method we had discussed before. But we just want to kind of see how can transformations be used for a similar problem, right? So again, for the first part, as you can see, it's a linear transformation. You have alpha beta roots of this equation, and now you want to form an equation whose roots are 2 alpha plus 3 comma 2 beta plus 3. So from what we've discussed, we just need to replace x by x minus 3 by 2. Right? So what happens? X minus in the original equation. So this then should be a required equation. Of course, it's not in the simplified form. You'll have to simplify it further. But essentially, the simplified form will give you the required equation. The reason why this essentially works is that, for example, how can you basically now show that 2 alpha plus 3 is the root of this equation? If you want to prove that, how can you be sure that 2 alpha plus 3 is the root of this particular equation, given that alpha is the root of this equation? That becomes pretty simple to see, because when you substitute x as 2 alpha plus 3 over here, what happens? If x is essentially 2 alpha plus 3, then x minus 3 by 2 happens to be the value alpha. So when I put x equal to 2 alpha plus 3 over here, the value of x minus 3 by 2 will be alpha. So the equation will finally reduce to alpha square plus 2 alpha minus 2. But that value clearly is 0 because alpha happens to satisfy this equation. So that is effectively saying that 2 alpha plus 3 as a value satisfies this given equation, and hence our transformation is correct. So if you just want to simplify this, I'll get something like x square plus 9 minus 6x plus 4 times x minus 3 minus 8 equal to 0. So that's finally reduces to the form x square minus 6x plus 4x, so that's minus 2x. And what else do you have? 9 minus 8 is plus 1. 1 minus 12 is minus 11 equal to 0. Right, so you got the answer pretty easily. You could have again just found the sum of the values and the product of the values also. Just to quickly verify that you would have got the same answer. So the alpha dash plus beta dash thing would have given you 2 times alpha plus beta plus 6, and alpha plus beta is minus 2. So that would have been minus 4 plus 6. So that would have been plus 2, and 2 alpha plus 3 into 2 beta plus 3. Right. So the sum of the values is turning out to be 2, the product of the values is turning out to be minus 11, so the equation clearly would have been x square minus 2x minus 11 equal to 0. Right? So the second part, the second part again can be solved easily using the idea of transformations. So just kind of give it some thought first, that how will you apply it. If it had just been 1 upon alpha and 1 upon beta, of course you could have just replaced x by 1 upon x, but now what will you have to do? The second part, you can kind of divide the problem into 2 steps. You can first find the equation whose roots are alpha plus 2 and beta plus 2, right? So first, as a first step, I'll replace x by, right? So replacing x by x minus 2, so first of all we are trying to get an equation with roots alpha plus 2 comma beta plus 2. So for that, from what we discussed, we have to replace x by x minus 2. So what do you get is x minus 2 square plus, so we get x square plus 4 minus 4x plus 2x minus 4 minus 2 equal to 0. So you get x square minus 2x minus 2 equal to 0. This of course is not your final answer. This again has roots alpha plus 2 and beta plus 2. Now we want an equation whose roots are the reciprocal of these two values. So effectively you want to find an equation whose roots are the reciprocals of the roots of this equation, not the original equation. So now again I will replace x by, right, so 1 by x square minus, so if I simplify this I'll get 2x square plus 2x, right? That is your final answer. So as you saw that we just kind of used a combination of the two transformations that we just discussed. First, we made the roots undergo a linear transformation, and then we kind of in the transformed equation that we got, we simply took a reciprocal of the roots by replacing x by 1 by x. In the third part again, just kind of take a moment and think about how can, so essentially again the two transformations that we've essentially discussed are linear reciprocation and a linear transformation. So for the third part again, you'll have to somehow reduce this transformation in terms of a linear and a reciprocation method if required. So the only thing that I have to do now again is, so my alpha dash is alpha plus 1 upon beta over here. So I can do something like this. I get alpha plus alpha upon alpha beta. But alpha into beta is minus 2. Right? So actually, so effectively, now the question becomes that, so this value is alpha 2 by 2 and this value is beta by 2. So you want to find an equation whose roots are alpha by 2 and beta by 2. That again is a linear transformation. Similarly, beta dash is beta by 2. So I'll replace x by 2x. So I get 4x square plus 4x minus 2 equals 0. So that's, so this should simply be your answer. And in the last part again, what you're doing is you are squaring your roots, which is actually not a linear transformation. But interestingly, you can reduce it to a linear transformation again. How? So again, alpha dash is alpha square. Now alpha is a root of this equation, so alpha square plus 2 alpha minus 2 should be 0, which will imply that alpha square is the same as 2 minus 2 alpha, which implies that the alpha dash that we need is the same as 2 minus 2 alpha, and the beta dash must be 2 minus 2 beta. So we've again reduced the fourth part to a linear transformation. So again, what do I have to do? Replace x by x minus 2 upon minus 2. So I'll get x square, then I'll get a minus 4x and minus 4x, so that's a minus 8x. And I'll get a plus 8 and minus 8, I'll cancel out, and I'll get a plus 4, so that's plus 4. Which again will be the same answer even if you were to use your normal method of alpha dash and beta dash. So it's not that any one method has a specific advantage over the other. This idea of transformation, the good thing about the idea of transformation is that once you start talking about cubics and higher ordered polynomials, then if you want to talk about similar problems over there, so maybe if you have an equation, if you have a given equation whose roots are alpha, beta, gamma, and you want to find a cubic whose roots will be 2 alpha plus 3, 2 beta plus 3, 2 gamma plus 3. Over there, the alpha dash, beta dash, gamma dash method that we've discussed over here might get a little cumbersome. But the same idea, the same problem through transformations will become fairly much easier in terms of the algebra involved, because you can do a similar thing over there also. So even if you have a cubic with roots alpha, beta, gamma, and you want to find a cubic with roots 2 alpha plus 3, 2 beta plus 3, 2 gamma plus 3, you'll simply say that you can just replace x by x minus 3 upon 2 and then just simplify the whole thing. So in that sense, the idea of transformations becomes much more is much better than the first method when you talk about higher degree polynomials. But at a quadratic polynomial level, both methods are equally no as such. One particular method is not really does not really have a huge advantage over the other. But again, you should know